So I thought it was about time that I built a little software-defined radio using the ESP32A1S, the Arduino environment, and the Arduino audio tools library that I've been using and playing around with in previous videos. In addition to the ESP32A1S, I'll be using at the heart of the radio this little Tayloe Detector board that I built up quite a while ago, and I'll include a link to the video, and it's got a link to the schematics for this. But this is effectively the receiver for the radio. Let's first start with a high-level block diagram of the radio that I'm building up. And there are two major components, and you can see them here on the left and the right. So on the left we have the receiver and the Tayloe board that I just showed you. This takes RF signals received from the antenna. It flows them through a bandpass filter, which in this case is configured for 20 meters or 14 megahertz. Those signals are then mixed with a local oscillator, and that was the SI5351 board, the blue board that you saw on there. And that emits the local oscillator signal at 0 and 90 degrees. So that gets mixed together with the incoming RF in a Tayloe mixer, which consists of an FST3253 acting as that mixer. And I'll include a link to kind of the paper that I've described earlier on Tayloe mixers that has the FST3253 in it. The result of that is it produces I and Q audio signals, which then are amplified and then exit the board through the audio jack. So the other major component is the ESP32A1S, and this is where all the control and digital signal processing happens. So just to sort of walk through the flow, those audio I and Q signals, which are produced by the Tayloe detector board, flow into the ES8388 audio codec, which is part of the ESP32A1S. And then that codec transforms those audio signals into I2S signals so that they can be consumed into the ESP32. So on the ESP32 we have Arduino running, as well as the Arduino audio tools library, and that serves to phase shift the I and the Q signals either plus or minus 90 degrees with respect to one another. And the purpose of that is to remove the unwanted sideband. The ESP32 also controls any other peripherals I want to use here, such as controlling the SI5351 through I2C to control the frequency of the local oscillator. There's also some other peripherals that I haven't got on here which the ESP32 will control, such as an encoder for changing the frequency, a display to show the display's frequency, and so on and so forth. So what I'm going to do is build this board up part by part and sort of demonstrate the functionality as we get through each of the parts. Just going through quickly the build and test order. So the first thing I'll be doing is connecting the SI5351 that's on the Tayloe detector board to the ESP32. I'll show you that connection, and then we'll run some simple Arduino code to show that it's outputting the 0 and 90 degree signals correctly. We'll then move on to creating a 90 degree phase shift, and I've done this before using the Arduino audio tools, and we'll show how that can produce the 0 and 90 degree phase shift for two audio signals. What we'll then do is we'll inject an RF signal into here, and we'll confirm that we get the appropriate audio output coming out here. And that will be at the difference frequency between the LO and whatever the received RF is here. And further, we should be able to control which sideband we want to receive. And then finally, we'll sort of all get it all together and put it on the air and listen to some actual stuff going on in 20 meters. So anyway, let's get started with the SI5351. I've used the SI5351 as an LO in many of my videos, so I won't go into depth on how to program it, but I'll include some links to those videos below. So what I'm essentially doing is using the EtherKit library which is up here. But I had to create a fork because that library only supports the default I2C port, and I needed to be running this off a different set of pins. So I include a link also to my fork in the description. One of the great things about using an SI5351 is that it does support emitting a pair of signals with a defined phase offset between them, which is exactly what we need in a Tayloe mixer. So you can see the code I've got here, and again, this is all up on the GitHub repo, so you can have a play around with it. And let me just quickly go through that code. It is relatively simple. So effectively what this code is doing is just looping between 5 megahertz and I think around about 40 megahertz, and it increases the frequency by 500 kilohertz every 5 seconds. So here's the meat of the how you actually control the frequency here, and you can see what I'm doing is I'm determining a multiplier based on the desired frequency, and there's like I said, have a look at the earlier videos on why you need to do this. But basically what you need to do is specify the desired frequency, which is F, this PLL frequency, and then which clock you want to output it on. So I'm outputting the same frequency on clocks 0 and 2, and then I'm using this set phase function. And what this set phase function does is this is what creates the defined phase offset. And you use mult equals 90 degrees. So basically that's how you control the phase offset between the two channels. Anyway, I'll include a link to my earlier videos because they've got more details on that. So let's have a look at this running in action now. Okay, so let's have a look at this. Let me try and draw some clarity for this rat's nest that I've got going on here. So the SI5351 board is mounted on the Tayloe Detector board, and it's connected to the ESP32 through this purple and yellow line, which is the I2C control lines from the ESP32. The I2C is set up on pins 19 and 23 on the ESP32. I'm probing at clocks 0 and 2 here, and obviously there's power coming to this board through these lines here. So again, let me just repeat that the code is actually starting at 5 megahertz, and every 5 seconds it increments the frequency by 500 kilocycles. So we'll go over to the oscilloscope and we should see that increment happening. Okay, so here we are on the oscilloscope, and freshly cleaned oscilloscope screen here. So let me just reset the ESP32, and you can see there that it's starting at 5 megahertz, and there it's going up in 500 kilohertz increments, and that works all the way up to 40 megahertz. And you can see the clock 0 and clock 1 are indeed 90 degrees out of phase with respect to one another. Now, I would put it in XY mode, but it's a kind of a square wave, so you're not going to see the perfect circle, but we do see I guess a semi-perfect square here. So it is indeed at 90 degrees offset there, so you could see that. And you know, one of the other great things about the SI5351 is it works pretty much all the way flawlessly on HF. You can drive it up to higher frequencies if you wish, but it works fine for my needs between 3 and 30 megahertz. So anyway, let's move on to the next step, which is just confirming that audio phase shift functionality that we've seen before with the Arduino audio tools toolkit. Okay, so now let's look at the phase shift functionality, which is in the example file streams I2S filter I2S. I won't dwell on this in too much detail. I've done that a number of times before, but basically what we have is 2 1 kilohertz signals in phase coming in into the ESP32A1S, and then that's processed inside the ESP32A1S, and then we have the phase shifted results, left and right channel, coming out the output here. And you can see as let me just pan up to the oscilloscope, those signals are indeed in quadrature, as you can see there. Let me just go to XY mode, the old circle test, and you can see those two signals are actually in quadrature. So let's move now to one of the things that you'll find is this is processed with 101 taps. So there's a certain limit to the amount of processing that you can do on the ESP32. And so let's see what happens when you cross that limit. So what I'll do is I'll change the code to run instead with 251 taps. And again, this is at 44.1 kilohertz. And you'll see the output, how the output changes. Okay, so we're back. I've flashed the board. This time we're running 251 taps of 44.1 kilohertz. And there you can see, this is what we'll see when there isn't enough processing horsepower and to basically do all the computation and keep the I2S stream going. So you can see the significant breaks in the output here. And if we just go to the speakers, if you don't have an oscilloscope, you can hear what that result is like. And that is obviously quite hideous, but that's the indicator that there's too much processing, and you need to either reduce the sample rate, 44 kilohertz down to say 16 kilohertz, or reduce the number of taps. Let me just turn that right down, it's quite annoying. So basically, we've got the frequency functionality, we've got the LO there, we've got the phase shift functionality. We're already sort of tied all together in the radio and inject a signal and see what we see. So let's move on to that now. Okay, so before we get to the radio, let's just quickly walk through the schematic here. And this is up on my GitHub repo. It's actually in KiCad, but I do have a PDF there if you don't have KiCad. So basically, this was taken from the previous video I did on the ESP32A1S, particularly with respect to the DTR and RTS processing for auto programming. So the changes you can see here. Here's the Tayloe board. And there's the I2C input into the Tayloe board. There's an RF in coming in here, and the output is an I and the Q signal. That I and the Q signal gets fed through a pair of 1 microfarad caps into line in left and line in right on the ESP32A1S. Just continuing, I'm taking audio out from the HP out R and HP out L. So that goes to out R and out L respectively, and then that gets processed, that gets output through this pair of 22 microfarad polarized caps, and then this simple low pass filter here consisting of a 330 ohm resistor and a 0.1 microfarad cap. Just continuing, I've got a rotary encoder switch here which serves the dual purpose of changing the frequency as well as the switch controls whether it's upper or lower sideband, and they're coming in through IO12 is used for the switch, and then the rotary encoder, it uses IO15 and IO4. Now just a note, I'm actually using the encoder library, and I'll include links to the encoder library, but that all works fine with Arduino. So just to continue, the other thing I've got is I've got an LCD display just to display the frequency, and that has an I2C backpack on it, so you program, you just sort of control the display through I2C, and that uses the same I2C pins that the Tayloe board is controlled with, so pins 19 for SCL and 23 for SDA. That's pretty much it on the board. I have included sort of a little reference up here for the various internal pins in the ESP32A1S. So let's now have a look at that board, and I'll walk through the various components on the breadboard. So here's the board. Let's just walk through some of the components I just talked about. So here's the ESP32A1S right here, and you can see there's sort of a rat's nest of wiring around that. I really do need to sort of mount this on a proper PC board. One of the things I am having trouble with is sort of a hum noise.
and I think it's to do with the fact that this isn't grounded properly. But anyway, so here's the ESP32A1S. We've got the LCD display over here, as you can see. Here's the line in. Here's the line out. This is the encoder over here. And then that's that pair of transistors that's used in the auto programming. And right here in the middle is the USB to serial. So that's basically all the components on the board. What we'll do now is I'll go over to the signal generator, and we'll just throw some signals at it, and we'll see how good its unwanted sideband suppression is. And that's coming right up. Okay, so let's have a look at the test setup here. We've got the signal generator, which is emitting a 14.2 megahertz signal at minus 70 dBm. Here's the radio down here, and let me just get this right, bear with me. Okay, so here's the radio here. It's tuned to 14.2, so wouldn't expect to hear a sound. So let's tune up. And there you can hear the tone through there, so that's a 1500 hertz tone because it's on lower sideband. So let's change to upper sideband. We should get a greatly attenuated tone there. Now you can still hear the tone. The other sideband suppression isn't as good as I would hoped, but let me be quiet and you can hear the difference between the two. So let me tune down now. And there's that upper sideband. So again, there's a RF signal coming out at minus 70 dBm. And I'm now on upper sideband, tuned to 14.1985. So that should be a 1500 hertz tone. Okay, so now I'm sending the audio output to the oscilloscope. It's now at minus 50 dBm, just so we could see the signal a little bit better. So I'm on lower sideband at the moment, same setup as before. The signal generator is emitting 14.2 megahertz. I'm on lower sideband and I'm tuned to 14201. So you can see there's that 1 kilohertz signal on the output as expected. So let me change to upper sideband. We should get greatly attenuated signal there. And you can see there's the greatly attenuated signal. Now, as I said, it's not quite as good attenuation of the unwanted sideband as I'd hoped, but anyway, it's not too bad. I'll get it on the air later on and we'll see that. So let's go back there. So let me tune down. So there's the crossover point. And then now I'm on lower sideband. Let me change to upper sideband. So let me just pan down so you can see what we're currently tuned to. So 14.199500 lower sideband. And now let me change to upper sideband. And then there's that signal. So I guess the next step is to get it on the air and see what we can hear. What I might do first is just quickly walk through the code. I know not everyone's interested in the code itself, but let me just walk through some of the code and some of the highlights in the code, and then we'll get this on the air for real and hear some 20-meter activity. Okay, so let's quickly walk through the radio code. So just to start with, I've included in the code a wide variety of different tap selections at different sample rates here, from 16 kilohertz all the way through to 44.1 kilohertz, and then a variety of different number of taps. And I generated these with that Hilbert Python program that I'll include a link to in the video. There's obviously some combinations here that there's not enough horsepower. Generally at 44.1 kilohertz, the most number of taps that I could get out of it was around about 161. I have been able to get 251 taps at 22 kilohertz. Now, there is a limitation in the Arduino Audio Tools toolkit right now that you can only the number of taps is uint 8, so you can only go up to 256 taps. So that's the maximum I could try here. But anyway, let's just scroll down and see what we can see here. You've seen this stuff before with the filtered stream. That's basically how you include an FIR filter in the Arduino Audio Tools toolkit. This channel add converter is something I had to add. One of the things that you do have to do when you're doing the processing is you either add left to the right channel or you subtract left from the right channel, depending on whether you want the upper or lower sideband. So I created my own converter, and I've included the code to that to facilitate that capability. Here's the encoder library that I mentioned. Now, the encoder library I used as is, and I'll include a link to the GitHub repo for that. The LiquidCrystal I2C, I had to create a fork for that because the one that was there, it was marked as only supporting AVR. I'm not sure why that it supports ESP32 fine, but also it didn't allow for changing the away from the default I2C pins, so I had to fork that. We've got this bounce library, which I'm sure you've seen before if you've done any button processing with the Arduino. It's a simple debouncer, a simple and effective debouncer. There's the SI5351, which we covered earlier. Here's where I print the frequency off. Not only print the frequency, but whether we're in upper or lower sideband. And just moving down, change frequency. You've seen that. That's that code that does the not only sets the frequency in the SI5351, but also controls the phase offset between clock 0 and clock 2. This is the standard sort of setup I2S here, which you have seen before. Setup FIRs, where we actually control what filter we're using here. So basically, if you want to play around with different filters, then you can just choose whatever filter you want, and this is where you slot that in right there. Setup synth we've had a look at before. Setup LCDs, just some simple setup code for that. This is where we set up the button that controls upper or lower sideband. Then we've got some setup code there. This was my attempt. I was getting a lot of noise on the. I was getting a lot of noise on the speakers, and one of my earlier suspicions was it was perhaps the Wi-Fi or the Bluetooth that was. So I tried turning them both off. Didn't make any difference at all. And then here's the code that reads the encoder using the encoder library to control the frequency. And then finally we've got a piece of code that is the push button for the upper and lower sideband control. And then here's the main processing loop here. It simply calls read encoder and then copy, which is the Arduino Audio Tools. That's the magic call that shuffles all the data between the I2S, the filter, and then this channel add, which was my addition that did either an add or a subtract left and right channel. So anyway, that's all the Arduino code. Like I said, it's all up on the GitHub repo if you want to play around with it. If you have any questions, I know some people have been having some trouble compiling these examples. Just let me know if you're having trouble. The Arduino Audio Tools is in active progress, so the author does make changes from time to time, and generally I try and keep up to date, but it is quite an active repo. So if there are any compilation problems with any of this, please let me know. I'm happy to dive in and fix it if I can. So anyway, let's move now to hearing this on the air, and that's coming right up.
Okay, so it's in the afternoon now, and the 20-meter band's starting to pick up. So let's tune around. Here's some signals.
Good Easy America Survey, Japan Echo, Echo America Survey, Japan Echo, and the calling California W7, California W7, Echo America Survey, Japan Echo, over.
Eu deixo de estar aí obscuro porque eu só disse aquilo a título de informação, não é? Porque de hábito não ouço nada, é tudo ali.
If you listen carefully, you can hear that sort of buzzing that I was talking about earlier, no doubt related to poor grounding of the ESP. Let me just turn it back up again.
Eu também era assim, e sem dúvida alguma, olha que a climatizador, isto tem que ser muito controlado.
So let's just swap between upper and lower sideband, and you should hear that signal be attenuated.
Par rapport à temperature.
You can still hear that signal, particularly the lower frequency content. Let me just turn it back again to upper sideband.
24, só 4 ou 5 graus, grande máximo, 5 graus abaixo.
So let's keep looking around.
Mike 0 Yankee Auto Florida 59, good night, thank you. Q100. Juliet Whiskey Charlie.
There's another signal close by. See if I can find it here.
Five over at 9. Good afternoon, Jerry. Stay safe. Thank you. Oscar Mike 3 Tango Whiskey Mike.
So anyway, that's a quick go around 20 meters. The band is reasonably active, but this has been a fun little radio. Obviously, lots I can do here. I think the main thing I want to do is sort of get this rat's nest onto a kind of proper PCB and see if that gives me some improvements in the audio quality. But anyway, I hope you enjoyed this video. As I said, all the stuff will be up on GitHub. If you have any questions on compiling or you get compilation errors or whatever, please do drop me a line. I'm happy to answer any questions. Hope you enjoyed this video, and that's all for now.